Now, using the Lagrangian approach, I don't really need to draw free body diagrams. I will only determine the energies in the system. First, I have two bodies, so I have two kinetic energies. So T will be the sum of the two kinetic energies for the two bodies. So 1 over 2 m1 x1 dot, the velocity squared, plus 1 over 2 m2 x2 dot squared. That takes care of the kinetic energy. The potential energy, we have two springs, so 1 over 2 K1, the stretch in spring 1 is x1, so that's x1 squared, plus for the second spring 1 over 2 K2, the stretch in the second spring is the difference between the x1 and x2 motions, so it's x2 minus x1 all squared. And here's the advantage. Now, if you assume x1 greater than x2, the sign here is flipped, and that really does not matter because anyway the bracket is squared. So this is where the advantage of this method is important. The damping or the dissipation function is 1 over 2 c1, and the velocity is x1 dot squared, and for the second damper 1 over 2 c2, the difference in speeds x2 dot minus x1 dot all squared again. So if you flip x1 minus x2, that's also the same. Now the degrees of freedom, Q is x1 and x2. So I will have to apply the Lagrange equation twice, once for x1 and the second time for x2. The Lagrangian is T minus V, which is 1 over 2 m1 x1 x1 dot squared plus 1 over 2 m2 x2 dot squared minus 1 over 2 k1 x1 squared minus 1 over 2 k2 x2 minus x1 all squared. Now Lagrange equation is d by dt partial L partial q dot plus partial d partial q dot minus partial L partial q equals partial work partial q, and the work in this case is we have one external force F causing a motion x2, so the work will be F times x2. So now first for Q equals x1, term by term, partial L partial x1 dot is all terms are zero that do not contain x1 dot, so it's only the derivative of the first term, which is m1 x1 dot, and taking the time derivative of this, d by dt partial L partial x1 dot equals m1 x1 double dot. Partial d, that's the second term, partial x1 dot is, here's the d function. So the first term with respect to x1 dot, the derivative is c1 x1 dot, and for the second term here, plus c2 x2 dot minus x1 dot, and the derivative inside the bracket, derivative of x1 dot is -1. So this is times -1. And the third term in the Lagrange equation, partial L partial x1, partial x1 equals the first term 0, no x1, no x1, and here's x1, so that's k1 or negative k1 x1, and here we have negative k2 x2 minus x1, and the derivative inside the bracket with respect to x1 is -1. The final term, derivative of the work with respect to x1 does not contain x1, so partial work partial x1 is 0. Now substituting these terms into Lagrange's equation, we will end up with the first differential equation of motion, which says that m1 x1 double dot plus c1 x1 dot, this becomes minus, so minus c2 x2 dot minus x1 dot, minus, so this is plus k1 x1 minus, so it's minus k2 x2 minus x1 equals the work 0. And this is equation of motion 1. If you expand, you will end up with the same equation of motion as with the one we got with the Newtonian approach. Now for Q equals x2, repeat the same thing. The partial derivative of L now with respect to x2 dot. The Lagrangian here, there's only one x2 dot term, which means that the derivative is m2 x2 dot, and the time derivative of this partial L partial x2 dot is m2 x2 double dot. The second term, which is the partial derivative of the dissipation function, partial d partial x2 dot, equals, the first term does not include x2 dot, so that's 0. The second term, c2 x2 dot minus x1 dot, and the derivative of x2 dot inside is 1, so times positive 1, and derivative of the Lagrangian with respect to x2 is just the last term, which is minus k2 x2 minus x1, and the derivative of x2 inside the bracket is again positive 1. And finally, the derivative of the work, partial w partial x2, and now this is not 0, it's f. And now we need to substitute all these terms back into Lagrange equation, and I will end up with the second differential equation, which says that m2 x2 double dot, that's the first term. The second term is plus c2 x2 dot minus x1 dot, and the third term is minus L, so that becomes plus k2 x2 minus x1, and finally that is equal to partial w partial x2, which is f. And this is the second differential equation, and these are the two ordinary differential equations describing this 2 degrees of freedom system.